Whoops. Well, it's a good thing you all are here. Okay. So what is the role of that? It's going to be our acid, right? If the hydroxide is our base, then the carboxylic acid, which is that functional group, is going to be our acid. It's the H+ donor. It's the thing that doesn't have the proton in the end. So then water is going to be our conjugate acid. Our carboxylate is going to be our conjugate base. All right? So if we're going to draw the curved arrows, we draw it from the base, that O-, to the H+. That hydroxide takes the proton. I know that we call the acid a proton donor, but it's more so like it releases it, and the base is more of like a proton taker, not just an acceptor. Like it reaches out and grabs that proton. And then we put the electrons onto that oxygen. So those are the curved arrows for our acid-base reaction. Which way does the equilibrium lie? That way, right? To the right. So when we look at this, you can compare the relative base strengths. The hydroxide is going to be a stronger base than our conjugate base. We'll talk about why, how to compare. It's going to be due to resonance, is going to be the ultimate answer. If you were using pKa's, the pKa of our carboxylic acid was about 5. The pKa of water is about 14. That's a greater pKa. That means it's weaker. So then we know that our conjugate base is going to be a weaker base. The hydroxide is our strong base. So when we do the next one, what type of reaction is this? Is this Bronsted acid base? No, there's no proton that's moving, right? So I know it's not Bronsted. So then what is it going to be? Lewis. Good. So we're going to start where we have electrons, go to where we don't. That boron has an empty p orbital. That's why it's our Lewis acid. The ether is going to be our Lewis base, that oxygen. Because that boron does not have a full octet, we don't need to have a second arrow going away from it. The electrons just go straight from the oxygen to the boron. So that is our product. This is known as a Lewis acid-base complex. That doesn't really matter. It's just they came together. Which way does the equilibrium lie? (50-50). To the right, yeah. So how we can know is boron has a full octet. Having that full octet is going to make it more stable. That makes it weaker. So now it's not as strong of a Lewis acid because it's more stable. Technically, all of our acid-base reactions are going to be reversible. If the change in the pKa between your acid and your conjugate acid is greater than 20, then it's considered essentially irreversible. So what I mean by this is we are going to use equilibrium arrows for all acid-base reactions unless we make a gas. If you make a gas, then you are truly irreversible because you produced something that bubbled out and disappeared. So if you make a gas, you're truly irreversible, then we use a forward arrow. For all of our acid-base reactions, we're going to use equilibrium arrows to remind ourselves that can always go backwards. Unless we have something as extreme as this. So this is one of the few cases where you could use a forward arrow. I'd be okay if you use equilibrium arrows because of my rule of just it's acid-base, so use equilibrium. So looking at this, what is my base? It's always the thing with electrons, right? So the thing with the negative charge. Just like how hydroxide is that O minus. Seeing that negative charge is telling me base. This is my base. My acid is the water. So I'm going to go from my base to my proton. Hydrogen can only make one bond, so I need to have a second arrow going away from that bond. That makes my conjugate acid, which is going to eventually be known as butane, and my conjugate base is hydroxide. Because I make hydroxide, you might think like, oh, that's a strong base, so the equilibrium should lie to the left. That's not correct, because it's not an extremely strong base. It's a strong base, but our carbon with a negative charge is going to be an extremely strong base. So we're actually going to, you could use that forward arrow because the pKa of water is 14. The pKa of our alkane, which is what this is going to be 50. That is a massive difference in our pKas. That's saying that as soon as that carbon takes that hydrogen, it does not give it back up, not readily. We're not going to see essentially any of this original starting material. It's going to go almost entirely to this. So you could use the forward arrow. All right, how do we rank these? We have 5 factors in order to determine our acid and base strength. They are the same 5 factors. You need to memorize these in order. I will always give you examples that use these 5 factors in this order. There are exceptions. There are actually quite a few exceptions. This will work like 80% of the time, and it'll cover you for every example I give you in this class. So charge is going to be our first factor, followed by atom, then resonance, then induction, then hybridization. We have decreasing significance as we go down. You are going to stop when you find the difference. What this is really looking at is comparing the stability of the conjugate base. So when we're looking at this, really, you can just use the bases as your point of comparison. Whatever is your more stable base is going to be the weaker base, meaning it came from the stronger acid. So when we look at charges, when you look at your compounds, if you are positively charged, you are going to be a better acid than if you are neutral, which is a much better acid than if you are negatively charged. The reason why is because for your conjugate base, it becomes neutral, which is better than being negatively charged, which is way better than having a 2- charge. That's why having your acid with a positive charge is going to be better, because it makes a neutral conjugate base. And if you are neutral, then you're going to be more stable. So when I look at these, the pKa of my hydronium ion, H3O+, is 0. Its conjugate base is water, that is neutral. The conjugate base of water is hydroxide. The conjugate base of hydroxide is oxide. So water, or the hydronium ion making water, is going to be the most acidic. We will never use hydroxide as an acid. It is a base. So that's why it doesn't have a pKa reported, because we don't rip that second proton off. We don't give it a 2- charge. We're not going to do that. Hydroxide will only be a base. It will never be an acid. If there's no difference in the charge, then you go down to the atom. The larger the atom, the more stable the conjugate base. So when we're going to use size, which is typically the more significant factor, as you increase the size, as you go down the periodic table, you're going to create a more stable conjugate base. The electron density on the larger atom will increase, but it's going to be spread out over a larger volume. Actually, so technically, I should say electron concentration. Concentration isn't a good word either. Number of electrons. We'll do it that way. The number of electrons are going to increase, but it's a larger atom, so it's going to be more stable. It's like if you have a mansion versus a studio apartment. If you have a mansion and you have a friend that needs to move in with you, that's not a problem. You got lots of space. You got plenty of rooms to put the friend in where they can take up space and not bother you at all. You're not going to bump into each other. You're not going to interfere. So if you have a mansion and you're a really large atom, you have a lot of orbitals, it's easy for you to accept an electron onto your atom. To just take an electron, you can put it wherever. If you have a studio apartment and your friend moves in, you are going to be really unstable. You're going to be trying to get that friend to find another home because it is going to be rather crammed and you're going to be bumping into each other a lot more. So it could still be possible, the friend could still move in, but it's not going to be as stable. So the larger atoms are more stable because they have more orbitals to accept the electrons. So larger atoms lead to a more stable conjugate base. So typically you will consider atom size before you consider atom electronegativity. When we look at our halogens, this is a really good example of atom size impacting it. As we go from our fluoride to our iodide, our pKa decreases, so we are increasing the acid strength with increasing size. That's when we are comparing the group, going down a group on the periodic table. So if you're comparing two atoms that are in the same group, in the same column, you're going to use size. When you compare two atoms that are in the same row, you're going to use electronegativity. As you increase the electronegativity, that's going to increase the stability of your conjugate base. Essentially, though, that atom is trying to pull electron density towards it anyway. So it's going to be really stable holding it because it's going to be attracting that electron density anyway. It wants it. So the pKa is going to increase as we go from right to left, or we should say the pKa will decrease as you go from left to right because you become a better acid as you go left to right. So we're going to increase our acidity with our increased electronegativity. Size is usually the more important factor, but if you're comparing in the same row, then you're going to use electronegativity. Size is not as significant when you're in the same row. For resonance, as you increase your number of resonance structures, or the quality of your resonance structures, that it's going to increase the stability of your conjugate base. You are spreading electron density out across the molecule. So when we compare that hydroxide to that acetate, we are having this resonance structure with that carboxylate acetate, where I can move the electrons up onto the other oxygen, whereas the hydroxide has no resonance. There's nowhere to put that electron density. It's stuck on the oxygen. So then you are increasing your acidity with increasing the number of resonance structures. Having resonance is going to make you more stable. A weaker base So therefore, you came from a stronger acid. When we look at induction, induction is the electron density that's pulled towards an electronegative atom, specifically through a sigma bond. So resonance, remember that's going to be the delocalization of electron density through unhybridized p orbitals. So that's spreading that electron density through p orbitals. Induction is through our sigma bonds. As you increase your nearby electronegative atoms, that is going to increase your stability of your conjugate base. So when we look at this, if I have just hydrogen compared to having a chlorine versus 2 chlorines versus 3 chlorines, each of these chlorines is going to be pulling electron density away from that negative. It's spreading it out more. So then it's going to make it more stable. The more you can spread out the electron density, the more stable you become, the less reactive. The weaker the base, the stronger the acid. So we are increasing our acid strength here with increasing the number of nearby electronegative atoms. It's important to note that the identity and the distance of the electronegative atom will also affect your inductive forces. So inductive forces are not as strong as resonance. So the farther away they get, the weaker they are. The closer they are, the stronger they are, the more significant they become. The farther away, the weaker the impact. So as we compare these, where I have chlorine really far away versus chlorine closer, compared to getting more electronegative atoms, I'm going to ultimately be increasing my acid strength with decreasing distance and increasing electronegativity. If there's no difference for the inductive forces, then you go on to consider your hybridization. Hybridization is sometimes just called orbitals because it is our orbitals. So hybridization meaning that we're talking about like sp3 versus sp2 versus sp. That's what I mean by hybridization, is we're looking at that relative character. The greater the S character, increasing your S character means that your negative charge is closer to the positively charged nucleus because your s orbital is smaller than your p orbital, so the s orbital is closer to the nucleus, closer to the center. So as you increase your s character, that negative charge, that electron density, gets pulled closer to the nucleus. That increases the stability of your conjugate base because opposite charges attract. So the closer you can get the opposite charges, the more stable it becomes. So when we look at how do I actually apply this, what is the hybridization of this atom? sp3, how do I know? 4 single bonds, beautiful. What is the hybridization of this atom? sp2, how do you know? Double bond. What's the hybridization of this atom? sp, how do you know? Triple bond, good. So when we look at this, sp3 has 25% s character because 1/4 of the orbitals that got mixed in were s orbitals. So sp2 has 33% s character because it's 1/3 of the orbitals. sp is 50% s character because it's 1/2 of the s orbitals, or 1/2 of the orbitals was an s orbital. So that means that we are increasing our s character, increases our acidity. So we're increasing our acid with increasing s character. Or you could just memorize that sp3 is weaker than sp2, which is weaker than sp. These are also, I should actually add these to the table. These are good values to have memorized as well. Like if memorization is your thing, then I would recommend knowing these as well, especially that 25 is getting kind of low. So alkynes we're going to see can actually be acids. We're not going to deprotonate an alkane or alkene. We're not taking those hydrogens. But an alkyne, if I have one of those extremely strong bases, that could absolutely take that proton. So our alkynes will actually be acids, not good acids. They're definitely weak acids, but they can be acids. So that's something that we want to keep in mind, especially when we get towards the end of the semester, is that our alkynes can be acids. That number is getting lower. That's low enough that I could actually find a real base to deprotonate. So when we are ranking the strength of our bases, it is the opposite of the acid, because now we're looking for the less stable or more reactive base. It is the same factors in the same order. It's just the opposite conclusion. So if I want charge, now I want that negative charge, which is better than neutral, which is better than positive charge, because now I'm more reactive if I'm negatively charged. For atom, now I want the less electronegative, or the smaller atom for the better base. For resonance, I don't want resonance if I want a strong base, because resonance stabilizes it, makes it weaker. So less resonance is going to be a stronger base, because now my electron density is localized. It's stuck. Now it's more reactive. I want to decrease my induction. That is going to give me a stronger base. If I'm looking at hybridization, then I want to increase my P character. Or you can think about it as decreasing your S character. Because now your electrons are farther from the nucleus. So now you're more reactive, less stable. So for the base, now its sp is less than sp2, which is less than sp3. So we're going to see negatively charged sp3 hybridized atoms are going to be extremely strong bases. So hydroxide is a strong base, but our extremely strong bases are going to be sp3 hybridized carbanions and sp3 hybridized nitrides, N-. So if you see those, just like how if you see one of your 6 strong acids, and that is protonate something, if you see this, deprotonate something, that is taking a proton. That is an extremely strong base. All right, so let's do practice problems. So we'll do the first one together, and then I'll let you do the rest on your own. So the first one, which one is the stronger acid? So to figure it out, we have those 5 factors. What's the first one? Charge. What is the second? Atom. Within atom, what are the 2 factors? Size and electronegativity. We have to have this memorized starting like now. What is 3? Resonance. What is 4? Induction. What is 5? Hybridization or orbitals. So some people, I've seen the abbreviation CARIO is the way that they memorized it, is just CARIO, so it's charge, atom, resonance, induction, orbitals. Do whatever you need to. I've had some people be like, what is it? Like cats are really into oranges, I think was one of them. Do whatever you need to memorize this. So make a mnemonic, whatever, but you need to know what it is and the order of them. That's what's most important. All right, so we do charge first. Is there a difference in the charge? No, they're both neutral. So 1, they're both neutral. That doesn't help me. So then I go on to 2. 2 is my atom. Is there a difference in the atom that the hydrogen is connected to? Yes. I have oxygen versus carbon, right? So when I compare oxygen versus carbon, now I found a difference. Cool, I stop. I'm going to now say, are carbon and oxygen in the same row or the same column or the same period or the same group? The same period, the same row, right? Carbon and oxygen, they're in the same row, row 2. So which factor do I use then? Size or electronegativity? Electronegativity, same row is electronegativity. So then do I want the more electronegative atom or less electronegative atom for the stronger acid? More electronegative. So oxygen is more electronegative. So then that is my stronger acid. You go factor by factor until you find the difference. When you find the difference, you stop. All right, so go ahead and do the next 2. When you think you got it, talk to the person next to you, compare and convince each other which one actually is the better acid. Compare the factors. All right, we got our answers. So for B, which one is the better acid, the left or the right? The left. So now we got to figure out why. So when we look at our charge first, there's no difference. Both are neutral. So then we go to the next factor. We look at atom. We're doing carbon versus carbon. That's the atom that the hydrogen is directly connected to. There's no difference. So I move on to the next one. Then I look at resonance. I'm looking at the conjugate base. So when I look at this, I am comparing that conjugate base versus that conjugate base. This conjugate base has resonance. So the molecule on the left is the stronger acid because of resonance. You have to look at the conjugate base when we're comparing the factors, especially for resonance. So then for C, which one is the better acid, left or right? The right, good. So which factor did you use? Yeah. Oh yeah, sorry. Yeah. So it's not just the fact that there's the double bond, it's the fact that the double bond is right next door. If I had drawn this, these two are essentially the same pKa's. That's a bad arrow. We'll just do approximately equal to. Because this has no resonance. So now these two molecules have about the same pKa because there's no resonance. So it's not just the identity of the double bond, it's the proximity to the hydrogen. It's the fact that when you make the conjugate base, you have the lone pair next to the double bond, then I get resonance. Cool, that's a good clarification. So for C, it's not induction. I mean, there's a little induction, and induction comes into play, but there's a more significant factor, so we got to go up on the list. Resonance. So when we look at our atom, when we look at our charge, it is both neutral. When we look at our atoms, we are comparing oxygen versus oxygen. That is the same. So then we're going to compare our resonance structures. So when I look at this, both have resonance, but one of them has a better resonance structure. So the one on the right has the resonance structure that is equal. These are equal majors. These are equal resonance contributors. Whereas the one on the left, you get this carbon with a negative charge versus oxygen with a negative charge. You get a major and a minor situation. So because of that, that's going to make these better resonance structures. So resonance is the factor of why this is the better acid. Because it's not just the number, it's also the quality of the resonance structures. Cool. All right. Have a wonderful day. Quick announcement. For the quiz, I'll say this in the quiz video as well, but for question 7, some of you, I actually graded the question itself because I was reading through, so if you completed the quiz early, then I actually just graded it. Most of you, like 80% of you, will see the quiz grade adjusted in the fudge points. So that means that the score that you get will be at the bottom of the quiz where it says fudge points. That's how many points you got for question 7. Okay, thanks.